All right, folks, welcome back. Hope you're all doing well out there. We are here for another segment of analytics for decision making, kind of working through our decision tree analysis of option value of information from last time. And in the last segment, we had worked through computing the expected payoff with no additional information other than the relative frequency data we had access to, which was given to us because we could observe the last 100 randomly chosen drill sites, where we recognized that out of the last 100 drill sites, only 20 of them were successes, which is why we have a 1/5 probability of success. And the remainder of those 100, the remaining 80 of them, were failures. 4/5 of the time, we did not strike oil after we sunk that $5 million investment. Okay, given that uncertainty, we figured out still investing and dealing with that uncertainty would yield us an average payoff, an average profit of $2 million, which was greater than the $0 certain payoff we could have assured us by not investing. Okay, so the optimal action without any information was to still invest, right? Randomly drilling, still drill. Okay, and when we did that, on average, we were $2 million ahead of where we would have been relative to non-drilling. So the expected payoff with no information was $2 million, and the optimal action with no information was to drill, was to make that investment. What we're going to do next is we're going to consider making the story a little bit more elaborate, in that we are going to be able to hire a geologist. And what the geologist will do for us is the geologist will provide us a report telling us whether or not a given site is likely to have oil in it. And to start things off as simple as possible, okay, we're going to start by assuming the geologist is as good as the geologist could possibly be. They provide a perfect signal, meaning the geologist is never wrong. And again, that test the geologist can be run before we're on the hook for committing to that investment, which means if the geologist were to give us bad news, we could back out. We're not held to making that sunk cost of $5 million. We'll assume that the result of the test provided by the geologist is an observable binary signal. This is going to make our tree diagram a little bit more complicated. In terms of the timing, the first thing that now happens is our geologist runs the test, and we're able to observe the realization of this test, right? We're able to observe a signal about the quality of the drill site. And it could be the case that they tell us, hey, this is a good drill site, indicative of a wet well. Or they might tell us, hey, we ran the test and it doesn't look like there's any oil in there, indicative of a failure. Okay, so they can give us one of two realizations of this binary signal. And for each of these realizations, we're then going to have to think about, well, should we invest or not? Given a good report, would I invest? Given a bad report, should I invest? And the answer to that question is going to depend critically on the quality of the geologist. The geologist is always wrong. You may not want to listen to him when he tells you things are good, but I'll come back to that point. The goal in this analysis is ultimately to find the value of the geologist report using the same three-step process we had applied in the Manhattan hot dog vendor example. And we started step one of that process in the previous segment by computing the value of the expected payoff with no information, which again was $2 million. So here is the situation. We could choose to not invest, which again nets us $0. And again, those two decision nodes that have the white circle with the hole in the middle, those are our decision nodes. That's where we have to take an action. And you'll notice there's not just one anymore, there's two of them. There's one for each possible quote unquote reality or universe we could be in, right? We could be in the alternate universe where they gave us a good signal, or we could be in the parallel universe where they gave us the bad signal. And for each of those contingencies, we want to be able to describe what does the optimal action look like. And again, following an investment, we do face the fundamental uncertainty of nature, right? But notice how I've relabeled some of these events. Okay, W given G, wet given that we had a good signal from the geologist. D given G, dry, given that we had a good signal from the geologist. And again, if it's wet well, the profit we make is 30. Dry well, we make a -5 loss. And again, those are all specified in millions. We also have to specify this at the bottom of the tree. If following a bad signal, we can invest. And now we have the conditional events, wet given bad and dry given bad. Right. And again, the dark circle, the black circles, those are nature's moves, if you will. Okay, so a little bit more complexity to the tree structure now, in that we have some timing to think about here. First thing that happens is we observe the signal realization. Then we get to decide, do we invest or not following a good signal? And do we invest or not following a bad signal? Once we decide if we invest, then we find out afterwards how nature's choice works out. Okay, so kind of 3 periods of interaction. Period 1, we just see the signal realization. Okay, period 2, given that realization, we make a decision. And then period 3, given that decision, right, nature randomizes some outcome. Okay, so in order to do this, we want to, again, remember our 3-step process where step 1 involves us computing the ex-ante expected payoff without the information that we're considering here. And this is precisely what we had done in the last segment and right at the beginning of this segment where we had revisited that and shown that the expected payoff with no information was $2 million. The next thing we have to do is we have to compute the expected payoff using the geologist. For every possible thing the geologist tells us, what should we do? What is our optimal decision for every possible realization? Okay, for every possible signal realization. If we see a good report, what do we do? If we see a bad report, what do we do? And then last but not least, we're going to compute the value of the information by looking to the extent to which the information causes our expected profit to increase. It's the same 3-step process, just a slightly more complicated example. Now, what makes this geologist a perfect geologist? Well, the geologist is perfectly informative. And we're going to be able to see this by looking carefully at our relative frequency data, gathered again on the same randomly sampled 100 random drill sites. But now we have a little bit more info. Not only can I see if one of those 100 drill sites was wet or dry, we can also see whether or not the geologist gave a good report or a bad report. Okay, so I want to be clear here. I'm going to show you some slightly different data, but the data has the same fundamental uncertainty as determined by nature, in that out of the last 100 drill sites, 20 of them wound up being successes, 80 of them wound up being failures. Okay, the difference now is we have another row in this table to think about, and that row corresponds to whether or not the geologist had given us a good signal or a bad signal. Okay, why is this geologist considered to be a perfectly informed geologist? It's because if his signal was good, okay, well, notice he's never wrong. every 20 of those wet wells, he gives a good signal for. Okay, similarly, every one of the 80 dry wells, this geologist correctly awards a bad signal realization to. He would give a bad report. Okay, so given the geologist good report, what's the probability that there's oil in the ground? Well, there's 20 good reports. How many of them involve a wet well? The answer is all 20, 20 out of 20. Okay, given a good report, how many are dry? 0 out of 20 are dry. So again, we should be able to just look right here, right? Given that we are in the good state, right? Meaning, given that we've already observed this realization, okay, there's 20 possible good signals that were given. How many of them involved wet wells? It was 20 out of the 20. Okay, and we can make a very similar argument at the bottom of the tree following a bad signal. Okay, given a bad signal, how many times do we see a bad signal? We see a bad report 80 out of the 100 times. Okay, how many of those bad reports involve a dry well? Every single one, 80 out of the 80. 0 out of the 80 involve a wet well following a bad report. So these tail end probabilities in the red here. Okay, I'm using the relative frequency approach to calculate these based off of this this matrix data in this table in the bottom left corner of the screen. Okay, you could also use Bayes' rule if you wanted to. In one of the later segments, I do that. It's a little bit more advanced, but you should be able to do this in an exam setting. Okay, use the relative frequency approach. That's what I really want you to be able to do. Let me simplify this just a little bit here. Instead of leaving all those fractions, let's just rewrite them as 0 and 1 because that's what they are. Okay, that is what we're going to refer to as the forecast accuracies, the posterior beliefs, right? Posterior after observing a good report. Okay, the probabilities at the bottom end of the trees, those are the posterior beliefs following a bad report. And because we know our geologist is perfect, right? What do we mean by that? How do I know he's perfect? I know that because the geologist in the data never makes a mistake. If the geologist were to make a mistake, there would be values that were non-zero here and here in the red circles. Right? If those were not zero, that means there's some cases where the geologist gave a good report, but it was a dry well. And there'll be some cases where he gave a bad report, but it was a success, a wet well. Okay, but we're dealing with right now a perfect signal, and the geologist is not making any mistake. Okay, I'm going to suggest that this is going to correspond to the maximum value of information that we can get from this problem. If the geologist was making any sort of mistakes, we may still listen to him, but the value of doing so is going to wind up being diminished. Okay, so let's go ahead now and think about computing the probability of observing either a good or a bad signal, right? What's the probability of a good signal? Well, there's 100 total days, 20 of them had good signals, right? But 80 of them had bad signals. So again, we should just be able to use this table and calculate the unconditional probabilities of good and bad and replace them appropriately. Right? A fifth of the time there's oil, geologist tells us exactly. So a fifth of the time we get a good signal. The other 4/5, we wind up getting a bad signal. Okay, so what we're going to do next is we're going to compute the expected payoff given that we've observed one of these two signal realizations. And we'll characterize the optimal action for each of those signal realizations. In order to characterize the optimal action, we're going to have to figure out the expected payoffs at each of the end nodes in this tree where nature is making a choice. Okay? And we're going to basically work our way backwards from the ends of the tree to the beginning. Okay, so let's start here by first assuming that we've observed a good signal from the geologist, meaning we are on the top half of this tree. Okay, if we were to invest, that puts us squarely up in this portion of the decision tree highlighted in blue. And if we were to invest, the expected payoff, well, we get 30 million with a probability of 1. We get -5 with a probability of 0. So hopefully it makes sense that our expected payoff given a good signal is 30 million. And since that's bigger than 0, we definitely want to invest following a good signal realization, meaning our optimal action at that decision node is to invest and listen to our geologist, right? We do not want to stay out in this case. Okay, that being said, what should we do following a bad signal realization in the event that we are put on the bottom portion of this decision tree, which happens 4/5 of the time? It's going to happen. Okay, 4/5 of the time they tell us bad, and we need to know what to do after bad. And again, we can compute the expected payoff here. I get -5 million with a 100% chance. I get 30 million with 0% chance, which means if I was to invest, my profit from investing after a bad signal will be -5 million. And I could always do better than that by just staying out and not investing. So my optimal action following a bad signal is no longer to invest. You might recall investing was also our optimal action with no information, right, from the previous segment. However, what we're going to see is that because our action has changed relative to what we would do with no information, that tells us the information has to have some option value. So when we compute the value of the information, because I see that we're not just investing no matter what, that's telling me the information is causing me to do something different in some situations relative to what I would have done without it, meaning it must have some value. Okay, if that bottom green arrow went down the invest track there, then there would be no value to the information. We'd be investing after a good signal, we'd be investing after a bad signal, and that's what we were doing anyway with no information. Okay, so we can start now to reduce some elements of this tree. And this will help us to think about computing the expected profit from using the signal. Okay, recall that after a good signal, we always wanted to invest, we always wanted to drill, and that's because we got a payoff of 30 million in expectation. So let's just replace that part of the tree with a 30 million expected payoff. We can do the same thing in the bottom portion, recalling that it was never optimal to invest following a bad report, which means we stayed out. So our profit using the info following a bad report wasn't -5, it was 0. We were able to avoid that loss, which otherwise we wouldn't have been able to avoid without the information, without our geologist. We would have just been randomly digging. 20% of the time we would be successful, but 80% of the time we wouldn't. Okay, here we're able to avoid that failure by listening to our geologist. And we can get rid of, again, the branches that we're not using here. And we could even reduce the tree a little bit further until we get down to the signal realization node, where we'll be able to compute the expected payoff using the information. So at this node, 1/5 of the time, we're going to invest, we make 30 million on average, but the other 4/5, after a bad signal, we stay out and we make 0. So you'll notice here, if we compute the expected payoff by weighting the green values with the associated probabilities, our expected payoff is now 6 million. And one major reason that is the case, why is it not 2 million? It's because rather than losing $5 million in a bad report state, we're actually able to avoid that $5 million loss by just not investing and taking a zero loss. Okay, so you might recall from earlier, right, when we did this with no information, okay, that minus $5 million payoff showed up, and that was dragging the average payoff down. All right, so with that being said, we're now in a position to compute the value, right, the option value of the geologist report. Okay, without the report, we were making 2 million, and our optimal action was always to invest. We just randomly drill. 20% of the time we'd be successful, 80% of the time we failed. But our optimal action was to keep drilling despite that. And when we did that, our payoff was $2 million. With the geologist helps us avoid some of those failure sites. And that causes our expected payoff to go up to 6 million, which you'll notice is a $4 million increase. One part of the story that we kind of abstracted away from was the cost of hiring the geologist. I did not include that in our analysis. We treated them as if they were free. But we can now think about, well, what's the most I'd be willing to pay for that geologist? Well, when I use them, they cause my profit to go up by $4 million. So the most I'd be willing to pay that geologist is capped at this value that they bring me, right? The option value of their information. In the next segment, we're going to discuss how to value an imperfect signal using the exact same methodology and example we worked through a moment ago. To do that, we're basically going to revisit that same pivot table or that confusion matrix that showed us the relative frequency of the past successes and failures of both our drill sites and the geologist signal. And we're going to think about changing that data a little bit, not so that we're changing nature's distribution of oil in the ground. We're still going to keep a 20-80 distribution of oil, but we're going to have our geologists make some mistakes given that distribution. And that is what we will talk about in the next segment. Hope to see you then.